Yeah, it's 4:02. I see a lot of people joined. I'm Christiane Blonowski. I'm a professor in the Climate and Space Sciences Department at UFM, and I'm the host of today's MIDAS seminar. Our speaker is Professor Vipin Kumar, and he's a professor, a Regents professor. Also, he holds the William Norris Chair in the Department of Computer Science and Engineering at the University of Minnesota. Vipin's research interests are highly diverse. He looks into data mining, high performance computing, how this applies to the climate sciences, also to healthcare. He was the chair or the PI of a big NSF expeditions and computing grant a few years ago, where they were pushing the understanding of climate change, a data-driven approach. And I bet we will hear a little bit about that in today's seminar. Vipin, as many of you know him, he's a highly accomplished scientist. He has written hundreds of publications and very popular textbooks, for example, Introduction to High Performance Computing or Introduction to Data Mining. Before we start with Vipin's seminar, let me also announce there are two more in the seminar series next week, April 12th and April 19th. So please also stay tuned for these seminars. We will now hear Vipin. It's about 45-50 minutes. Please, if you have questions, use the Q&A box, and we will then entertain questions after the seminar. So Vipin, the floor is yours. Thank you.
Very good. Thank you, Christiane, and pleasure to be here in virtually, given the circumstances. So my talk is about, I'm trying to get my, yes, okay. So this is about the excitement that we sort of all hear about machine learning and its application in sciences. And the question is, can we make these machine learning algorithms aware of the physics or be guided by the physics? Again, the backdrop is that the big data and machine learning have revolutionized all aspects of our life, and they are increasingly being considered as alternatives for accelerating the traditional scientific discovery paradigm. And again, this is not coming from a computer scientist, but it's sort of coming from the scientific community, places like Nature and Science, and then of course NSF has harnessing the data revolution as one of the 10 big ideas, and whose objective is again to accelerate the methodology of scientific discovery using what we have learned from the machine learning successes so far. And increasingly, machine learning is being applied in all areas of science and engineering as we speak. But there are many, many instances in where we sort of see the black box method, as they're called in machine learning, because they tend to only work with the training data and sort of find the relationships inside them. But these black box methods have often shown disappointing results, not always, but many, many times. And again, some of the issues that people experience, of course, is one of them is that some of the state-of-the-art machine learning algorithms require tremendous amount of data. A lot of the successes and excitement that has happened recently is coming from the deep learning methodologies, and those are massive models, lots of parameters, and you need huge amount of data to train them. The second thing is when you apply them to scientific domains, you could often generate results that are physically consistent. And in the physical world, there are certain expectations you have from what you're seeing, and if those are not met, then that's a good sign that what you're learning is perhaps not quite right, or is going to fail soon. And the third thing is, which is a pretty serious problem, is that they can often fail to generalize to unseen scenarios in the sense that machine learning algorithms find patterns in the data that you give them for training, but oftentimes you need to apply them to situations that are unseen. So out of sample generalization is a huge issue, which of course is not an issue with mathematical models for the most part. And the last part is that even if machine learning models do really well, they often are unable to provide valuable physical insights. And then all of these problems sort of coming together have sort of tempered the excitement of the use of machine learning in scientific domain. And one of the poster child of an application like this is the Google flu trend. That's sort of a application that Google designed to basically predict the outset of pandemic, about the flu outbreaks, not the pandemic, flu outbreaks, about 9 years ago, just by looking at the search queries, and then they were able to do that a few weeks before CDC would announce the flu outbreak. And that's considered to be extremely important milestone, but pretty soon what it turned out that as the times went by, in a few years, by the next year, the model started over predicting, and of course became pretty clear that the model is not very useful, and it has been decommissioned since then. So basically, this is where we are. So again, just sort of to assess the state of the art in this area. So you have two different types of communities using two different types of models. One of them is the data science models that, of course, people in computer science have gotten used to developing and seeing them greatly successful. And these are the models that are extremely successful when you have lots of data. They basically can be considered as knowledge-free models, or sort of, you don't need theory, you just can work with the data. And there are situations, there are actually applications like language translation and computer vision, where decades of theory developed in linguistics, for example, has been superseded by these translation models that simply make use of trillions of texts available, sentences available on the internet, and they do a phenomenal job, much better than what you could do by these linguistic theory-based models. Then on the other hand, but on the other hand, these models have tremendous issues when the data is not representative, the data is not plentiful like it is in the case of language text, which happens to be plentiful. Then on the other side, you have the scientific community where they sort of build these mechanistic models, process-based models as they're often called, and these, and if the models are perfect and if they're able to do a really good job of representing the reality at the level of detail that we're interested in, they do a really good job. But oftentimes they are limited by our current scientific understanding, or very often they have large number of parameters that they have to be calibrated, and calibration of those parameters requires data, and then not enough data is available to calibrate them. So again, we have two situations, one in which you have enough information, enough scientific theories or knowledge about your problem, in which you can you have really good models and you can get by, but you are limited because of the incompleteness or the approximation of those models. And then on the other hand, you have these data-driven models that really do phenomenally well if you have plenty of data. So basically, what we're looking for is looking at are the two different paradigms. Each of them make use of incomplete sources of information about the two key components of knowledge discovery, the theory and the data. What this talk is about is this theory-guided data science paradigm in which you're trying to leverage the data along with the scientific theory, but you want to use the scientific theory, but also use the latest advances in the machine learning and the data-driven modeling techniques. So basically, this paradigm actually, people started talking about it, in starting about 7-8 years ago. I mean, our group wrote a paper as far back as 2014, 7 years ago. But then this paradigm has really taken off. The business of sort of bringing machine learning and the scientific knowledge has sort of come about in lots of disciplines. Every scientific discipline you can think of, people are sort of talking about merging these two areas together. And it's often this area sort of goes by knowledge-guided machine learning, science-guided machine learning, physics-guided, physics-informed, physics-aware. There are all sorts of names people have used from time to time. And we're going to use these terms sort of interchangeably. And as I mentioned, there is not a single application domain that you can sort of think where this area is this kind of merging of scientific theory and machine learning is relevant. And very recently, we finished completing a survey of integrating physics-based modeling with machine learning. And this survey basically surveyed about 300 papers, nearly all of them published in the last 3-4 years at the intersection of this paradigm. So this is a very popular paradigm. There are agencies with programs in this area, physics of AI, or the CCC Computing Consortium did a 20-year roadmap about a year ago and about 2 years ago. And then they had a big section on accelerating scientific discovery using such techniques. In 2020 alone, there have been many workshops and conferences. One of them we held at the University of Minnesota last August. There were over 1,000 people registered for the workshop from 30 plus countries. So it's a very popular area and very relevant, very timely. So in this talk, my objective is to give you a little bit of an overview of this area, and while sort of trying to answer some questions that would be of interest to anybody who is interested in bringing scientific theories or scientific knowledge along with machine learning. So the question is, some of the questions that, of course, and many of these questions are being considered by a lot of people in different domains, but I'm just sort of paraphrasing them here, summarizing them here. Can physics-guided machine learning models outperform pure physics-based or pure mechanistic models? And then, of course, when you say something outperforms pure physics-based model, it can sort of, one of the first things you would sort of say is, well, does it provide me better accuracy with limited observation data? And of course, if I had plenty of observations, it might provide me better accuracy, but does it provide me good accuracy, better accuracy with limited observation data? Can you produce results? Can they produce results that are physically consistent? Can they generalize to unseen testing scenarios, say the out-of-sample generalization? So these are all the key questions that are very, very relevant. Can you model processes that are unfolding at different scales? Most of these scientific models are modeling phenomena, and you have multiple processes that are involved in it, and they always interact. And then these processes are sort of happening at different scales. Can the machine learning framework handle that kind of thing? Can you assimilate information that becomes available as opposed to the traditional machine learning paradigm in which you get the training data, you build a model, and then you apply it to the unseen data? Can you create data at higher resolution? Some of these things become very, very important, for example, in the pandemic planning and in climate simulations and such. Can these models provide new insights beyond what you would be able to get just from pure machine learning models or pure process models? Can they be useful even in absence of observation data? So all sorts of questions are being studied, and of course, many of them are being studied by us and by many other people across the scientific community. Today, I am going to discuss these in the context of two environmental applications. One of them is modeling the lake temperature dynamics. I guess Michigan is in Midwest, and in the Midwest, there are literally hundreds of thousands of lakes and water bodies. And USGS, the United States Geological Surveys, is responsible for monitoring the health of these water bodies, and these water bodies are changing in response to human actions and changing climate. And one of the things that sort of impact these lakes is the dynamics of the temperature. That is how the temperature profile changes in the lakes, which is very critical for determining the health of these of the fisheries and the other species. And the water is used in these lakes for recreation, and the temperature water quality, it sort of depends upon the temperature of the water and a whole host of other things. So this is one key application, and then this is we're sort of working with USGS directly on building these process-guided machine learning models to improve the modeling of the lake systems. And the other application I'm going to talk about is coming from hydrology, where you're looking at the response of a hydrological basin in response to the changing weather and human actions. And one of the physics process-based model that's used there is SWOT. It's a model used by the hydrological community. And for the lake temperature modeling, I'm going to sort of use the GLM as the physics-based model, which is used in operational sense by the USGS. So that sort of sets the stage for my rest of the results that I'm going to present. And the first set of results in this context of bringing physics and machine learning together would be in the context of lake temperature modeling. And here the idea is that you want to be able to figure out in response to the meteorological drivers like temperature, precipitation, humidity, wind speed, and so forth, as they're sort of changing every day, what's happening to the column of water, the temperature of the column of water in any of these lakes. And as I said, how the temperature changes has a huge impact on what species of fish can live in those lakes, what sort of fish, when the invasive species can survive there, or what would be the quality of the water, and a whole bunch of other issues that are very, very important. And in this particular case, you can have the information about the drivers is available from various sources, including NOAA and NASA, about the weather drivers. And then for many of these lakes, I should say for some of these hundreds of thousands of lakes, we have enough amount of observation data. For example, there's a Lake Mendota where the USGS data science headquarters is located in Madison, Wisconsin. And they have, for the Lake Mendota, observations going back almost 30 years, frequent observations at multiple levels of the depth. So this is a situation which is ripe for potentially building a machine learning model in which you have the weather drivers coming in from the traditional sources, and you have the black box model here, which could be, of course, a neural network, but could be anything else as well. And using the weather drivers, it could sort of make predictions for the lake temperature at different depth of the lake. And you have the observations, which are the label data available in some cases. And then you can sort of figure out if you can try to build a model where the predicted value happens to be close enough to the observation. So basically you compute the training loss. And if you're using neural network or some sort of an LSTM, because given that it's a time-based system, your training loss could be, your overall objective could be minimizing this training loss, but also regularizing the complexity of the model, which is a standard technique that's used in machine learning to make sure that your models don't overtrain for the data. So this is a traditional methodology used very extensively in many applications of machine learning. And the challenge that it faces in being able to capture the dynamics of lakes, and for example, even in places where you have, in sort of situations like we're talking about, being able to monitor these hundreds of thousands of lakes in the US, is that the labeled data is scarce. For some lakes, you have plentiful data, but for vast majority of the hundreds of thousands of lakes, you have very, very few observations. Actually, there are only about 500 lakes for which USGS has data for more than 100 days. There are 95% of the lakes for which you have only 1 or 2 observations or maybe no observations. So that becomes a big issue. Second challenge is that when you're predicting water temperature at different depth of the lake, it can become physically inconsistent, especially if you're coming out of a machine learning model. Temperature connects to density, and density, of course, should be such that denser water should be at the bottom. And if a deep learning model, which is trying to optimize the training loss, may end up producing results which are not necessarily physically consistent. The other thing is the lake are warming or cooling in response to the energy flux coming in and energy flux going out. And the difference between the two energy is what determines how the lake should be warming. And it's not necessary that the machine learning model that predicts the temperature of the lake at different time steps would sort of follow the conservation of energy in the sense of making sure the flux of energy in and out corresponds to the change in the energy budget of the lake. So now the question is, how do we handle it? Well, it's easy to, in such cases, to add a component to the training loss, which is the physics-based loss, which can be computed based upon the terms that are relevant from the physical perspective. And once you do that, you have a hope. If these are sort of course soft constraints, but you have a hope that you can produce results that are going to be physically consistent. And these loss could be sort of just based upon the observations, like the density depth constraints, or the loss could be based upon the energy conservation, which means that the neural network will have to keep track of the flux of energy coming in and out at a given time, and and also keep track of the change in the energy of the bowl, of the lake, to compute this last term. The idea is that this last term is completely physics-based and the other terms are purely data-based. Now, the big advantage of having this last term is that you have a better hope of predicting results that are consistent, and we'll see whether you can achieve that. But a bigger additional advantage is that by having this last term that are physics-based, you also have the opportunity to do the training of your model even in absence of the true observations. Because if you don't have the observations, you always have the drivers, and you can feed them through the network and compute the output, and you can still compute the physics-based laws. So physics-based laws can be computed at any time step, which means you can do training even on time steps when you have no observation. So that's basically the bonus, the advantage. And this is how the LSTM, the deep neural network, would look like for modeling the lake temperature. And if you look at the black part of this picture, this is the standard textbook LSTM model. And if you look at the blue portions of this image, those are the portions that are adding in the physics. The blue portions are the ones that are capturing the energy terms and computing the lake energy change from time step to time step, and then using them to compute the extra loss term, the physics-based loss term. Still pretty close to the standard methodology that's used in machine learning. Now, the question is, could we, this model, of course, bring in the physical information, but these physics-based models actually also produce infinite amount of label data in a synthetic scenario, in the sense that any physics model is going to be taking the labeled, the weather drivers, and is going to produce is going to produce the output, and the output, of course, will be synthetic output. It's not the same thing as the real observations, but one could use those physics model output produced by the physics-based model as a synthetic labels and use them to initialize the machine learning model. So in some sense, to use them to sort of initialize the model. And then, of course, then you can, once this model is sufficiently trained, it can be fine-tuned using the observation. So basically, then this becomes an alternate approach or alternate ways in which these physics models can be used to sort of jumpstart the machine learning model. So in some sense, there's yet another way in which the physics models can sort of serve as a teacher for the machine learning model. And this is a technique that sort of works extremely well. So now let us see how these two different ways of sort of bringing the physics models to help the machine learning models sort of help correspond relative to the pure process-based models and a pure machine learning model. So again, I'm sort of bringing you to the it's very specific scenario of modeling the dynamics of the lake temperature in Lake Mendota, which is, as I said, we have plenty of data, thousands of days for which we have high quality data at every depth or many depths of the lake. And for this, if you use the GLM, which is a process-based model, it's sort of, if you don't calibrate that model specifically to this lake, it's very high observation error. The vertical dimension here is showing you the RMSE. It can be as high as something like 3.5 to 4 degrees, for reasonable parameterization. But as you use the observations, some of the observations of the lake to parameterize to find the right parameter for the model, the performance improves, the RMSE goes down. And as you go up on the Y dimension, the RMSE is going down, as you see. And after you have seen sufficiently many samples, it sort of stabilizes at a point of about 1.8 degrees RMSE, which is decent, but not good enough as far as the USGS is concerned. For example, they like to, these errors could be even lower. Now, if I build a pure machine learning model of the kind that I showed you before, not the physics guided model, but the pure black box LSTM, standard black box LSTM. Of course, if it has no data, then of course it cannot learn anything. But as you increase data for more and more days, eventually its performance supersedes that of a process-based model. And actually for 1,000 days worth of data, its error actually goes down quite a bit lower than the pure process-based model. It gets close enough to about 1 degree centigrade, which is actually pretty good performance. But as I said, Lake Mendota is one of the very few lakes, maybe about a half a dozen or so lakes, for which you have as many observations as the one you're looking at, like thousands of observations. So that's actually a very rare thing to have. So now the question is, how would the physics-guided machine learning model that we just talked about, how would they perform in this scenario? And that's going to be my last, this purple color, which is the process-guided machine learning model. And then you can sort of see here, now this purple model is doing most of its learning from the green model, which is a process-based model, because it's running from the synthetic data. And then getting even a very small number of observations, 2 days worth of data vertically at each depth of the lake, can already increase the performance to a level where you will need huge amount of data even to train the process-based model. And I think you can sort of see that with a couple of dozen days of data, about 10 to 15 days of data is doing actually really, really well, about as good as you can do with any of the other models. So this bringing the process and the machine learning together, the process knowledge and machine learning together, is actually able to give us both, give us actually much better performance at very, very small number of samples. So that's the first advantage that you see here. The second thing is, as I mentioned earlier, the biggest concern in any physical modeling is to be able to see whether we can perform, how well we perform in novel testing scenario. So the result that I showed you earlier were the cases in which you have data for multiple decades. You use some of those decades for training, and some of the other decades, a different part of the time period for testing. And the expectation is that the training and testing periods are not terribly different from each other. So here I'm going to show you the results in which there are 2 sets of results here, and the right set of results actually are the ones in which you're talking about testing in novel scenario. So the left side is the one in which the training and test are similar, but in each case, what you're seeing here is the performance of all of the 3 models being trained using 500 days of the observations. So these 3 points that you're seeing here come directly from the chart that you saw on the previous slide, where of course you saw that the process-guided deep learning actually does better than pure machine learning or pure process-based model, but pure deep learning actually does a pretty good job. It does slightly better than process-guided model. On the right half of this figure, what you're seeing here is in which all of the 3 paradigms were given for training only the data from 3 seasons, spring, fall, and winter. And every one of them during the training period did not have access to the observations from the summer period. Okay, so you can sort of see here that if the pure machine learning algorithm does not see anything about the summer, and summer in Midwest can be very different than spring and fall and winter, so you can see that this pure machine learning model dropped in a big time in performance because it had no access, it had no understanding of what the summer is. Okay, but even a pure process model dropped quite a bit too, because process models also have parameters, and those parameters got calibrated to suit only spring, fall, and winter, and they had no idea as to what the summer looks like, and what sort of the right value would be for the summer, so they dropped as well. But amazing thing is that the machine learning model that learned mostly from the process model, that means it learned the structure from the process model and was not shown the summer observations, dropped also, but very little, and actually the gap between this and the other ones became much more dramatic, as you can see in this picture, than in the case of the regular testing scenario. So this sort of gives us hope that yes, this physics-guided machine learning paradigm is able to go to novel testing scenario. The last slide, this next slide, is just trying to show you that yes, the process-guided machine learning model is also able to maintain the energy conservation, just like a physics model would do. So this is the GLM. This is the process-guided machine learning, which has the energy conservation built into it. And this is the standard RNN, which is the black box machine learning model. And what you're seeing here is the 2 different terms that they're being computed. One of them is flux of energy. Green is the flux of energy coming into the lake and the flux of energy reflected back from the lake. If you take the difference between those 2, that should match the change in the energy budget of the bowl. So blue is the change in the energy of the bowl from one day to the next. And the green part is sort of telling you what was the difference between the flux of energy coming in and out. They have to match. And you can see that for both of these, the process model, of course, it matches by definition. And the process-guided machine learning framework also matches it pretty decently, pretty good. It's not a hard constraint. It's a soft constraint, but does a pretty good job. And of course, standard RNN has no clue. So there's no match between those two terms. Even though it can perform, it can reduce the RMSE, it can make the temperatures match, but the energies is not matching at all. So this gives you a sort of sense of the power of these different algorithms, the process-guided machine learning algorithms in addressing the issues of small number of labels, being able to generalize to out-of-sample scenarios, and being able to conserve energy and so forth. Okay. Now the next question one could ask is that the system that I showed you is a relatively simple system, although it was considered by USGS to be very important, because using this paradigm and a few other advances, they now are able to use this paradigm to model literally tens of thousands of lakes around the US. In the sense that for tens of thousands of lakes, they have small amount of data, and using this paradigm, they can sort of show that wherever they have observations, they can show this paradigm does dramatically better than either process-based models or pure machine learning models, which means it gives them a hope that they can actually use that framework to go out and monitor all of these hundreds of thousands of lakes that are out there. But now the question that I like to sort of answer in the next 10, 15 minutes, or the rest of my talk, is I've showed you one way of bringing physics into the machine learning model, which is augmenting the loss function. It's the easiest way of bringing in physics into the machine learning model, because it just, as a physical scientist, you would sort of know what physics is relevant for your application. And it's very easy to code it into a loss function. And then you can stay pretty close to the standard machinery. But it turns out, and by the way, this way of including physics into loss function is literally the most popular way of bringing physics into machine learning. And if you look at our survey of 300 papers, more than almost as many as half of them use this methodology. Now, that is, it's a very popular methodology. It's a very easy methodology, very good methodology. But the question is, are there other ways that make sense to incorporate physics into the machine learning model? And I'm going to try to answer that question using this somewhat more complex model. It's a hydrological model. I'm trying to model the flow of water that's coming out of a watershed in response to the rainfall in the watershed, in response, and which of course depend. This basically, as the rain falls in the form of water or snow, some of it gets absorbed in the soil, some of it sort of goes underground, some of it sort of falls laterally, some of it gets evaporated by the plant. There are all sorts of processes that are involved in a watershed before you sort of see the water sort of flowing down a river stream. And there are complex models. There are literally dozens and dozens of models that are very popular, used all over the world for modeling these high-level systems. And increasingly, of course, these models have parameters, and then people are always unsatisfied with their performance. So machine learning has been used very effectively, or use of empirical models, as they're called in hydrology, is very common. And more recently, people have started using deep neural networks. And what we have just talked about is, if you look at the lessons that we have learned so far, I could simply replace this process model by a deep neural network, which could even be a physics-guided neural network along the lines we talked about, in which I sort of feed in the weather inputs and I watch for the stream flow, and I get the observations for a certain watershed, and use the observations to basically train my model, and then hope it'll be able to predict into the future. So, and again, any of the lessons that you talked about, being able to use pre-training, being able to sort of bring in the physics, all of them can be brought in here. But this black box model is still sort of treating the entire weather drivers as an input and trying to predict the quantity of interest. So the question is, what else could be done potentially in a situation like this? And one thing that's very important is that anytime you're trying to model a physical system, oftentimes, of course, you have multiple quantities that are sort of changing that are impacting the physical system. And you're trying to model a specific quantity. In this particular case, you may be modeling stream flow, which of course is very important from many perspectives. But as I mentioned earlier, in a hydrological basin, there are many, many other processes that are also happening, and collectively, all of these processes are responsible for the stream flow. So there's a precipitation, there is a snowpack, there could be soil, moisture, the state of the soil, there could be amount of water that's flowing laterally, there's a base flow, evapotranspiration from the plants. There are all sorts of processes that are sort of happening, and they're all being modeled by a process model. So reality is always much more complex than just the one variable that you're trying to model using a machine learning framework. Now the question is, could you potentially model all of these variables simultaneously? Now, in general, if you try to build a machine learning model and make it optimize multiple things, its performance on the thing that you're trying to optimize potentially could go worse. So for example, if I take the traditional machine learning approach, and if I try to model all of these different processes simultaneously, then it's entirely possible that my performance on the specific target of interest, stream flow, could actually become worse as a result of modeling multiple things. It certainly would happen in the training phase, but it could also happen in the test phase, depending on how well this thing is done. So it turns out that if the simultaneous modeling is done properly, then in the training phase, you might do worse on the stream flow compared to the other model. But in the out of sample scenarios, in the testing phase, actually you can show, and you will see the results that actually you can do much better than just modeling only one variable. So in some sense, you've made your problem harder, and yet you can do a much better job on this harder problem because you're trying to solve multiple components of the system that are interrelated. And by having to solve all of them simultaneously, you're doing a more robust job on the target value of interest. So it may seem counterintuitive, but actually it does a pretty good job. Second thing is that when a black box machine learning algorithm is building a model from all different inputs and computing the stream flow, it's treating each one of those variables at a similar level. That is, each one of those variables come in a training record, and those values get fed in to the multi-layer network, and you're computing the loss, and you're sort of backpropping the information. Except that these variables that are being fed into the deep neural network actually are of an entirely different nature. Okay? Some of them may be states, some of them may be fluxes, some of the fluxes are changing every day. Like for example, the precipitation could be changing by the hours, whereas the state of the soil could be changing much more slowly. So in a physical system, you often have variables that are sort of changing at different rates. And for your machine learning algorithm to be cognizant of that is very, very important, in the sense that if you bring that information into the machine learning framework, you have potential to improve the performance of your modeling. Third thing is, these different variables actually are interdependent. They're not just half a dozen variables being sort of modeled independently. They feed into each other. And if you leverage this dependent structure in the architecture of the machine learning model, that could actually help as well. Fourth thing is there are physical constraints that exist among these variables, like mass conservation, and all sorts of other things. And bringing those in can actually improve the performance as well. So basically, these are sort of the different ways beyond what we just talked about in the context of lake temperature modeling that you can bring in to improve the machine learning models that are sort of process guided. And on the next slide, I'm just showing you that there are large varieties of ways all of these ideas can be sort of brought in. I don't have time to go over them. It's something, it's a work in progress, but you'll be happy to share this work with you, those of you who are interested. What I'm going to show you next is sort of result of some of these methodologies on a real data set. And again, I'm going to show you two different sets of results. One of them is a basin, a south branch of the Root River, Garden Meadow in southeast Minnesota, It's a simulation, a SWOT model simulation for 1,000 years. So all of the results that you're seeing here is synthetic at this time. And the question is, given that SWOT can produce this input and output pairs, the weather drivers and the stream flows for 1,000 years, can we then replicate it in a machine learning model? And of course, what we're doing here is we're using the first 600 years of this data for training, last 400 years for testing, and other parameters, of course, mentioned here on the slide. And what you see here is that if I treated the standard LSTM, which means I have the weather input, and I just compute the flow, I have a pretty high error, about 0.63, and let's say whatever it is. But if I try to optimize multiple parameters simultaneously, not in just the stream flow, but evapotranspiration, soil water, and snowpack, and leaf area index, multiple variables. And if I do them properly, if I don't do them properly, the performance actually becomes worse. My performance actually gets better. If I treat the variables that are changing slowly versus fast, like state versus fluxes, my performance gets even better. And of course, if I use the hierarchical structure among these relationships, it gets even better. And then what you can see here is for two of these results, the second one, the green error profile is shown on the right side. And for the red one, the error profile is shown here. So basically what I'm trying to show here on the right side is the profile of error on different days of the year. And you can see that some of these other models were actually giving high error all across the year, but this two-layer LSTM with hierarchy and state awareness and everything is actually doing a pretty good job in much of the summer, still giving some error during the winter time. And it's because the snowpack process is not being modeled as well as it could be. So the point of the slide is that there are many aspects of the physical system that can be brought inside the machine learning framework, improve the overall modeling. And this is sort of, this is the kind of thing that can't be done by a pure machine learning framework with standard methods for incorporating physics, but it has to be something that has been done by a collaborative setting with a data scientist and a physical scientist. The other experiment I'm showing you, this is actually a very famous data set that hydrologists use. This is for the entire United States. There are 531 basins for which they have data for 35 years. They have simulation data, observation data, multiple things, but here I'm only showing you results for the simulation, and then the same methodology was applied on these 531 basins. And in this particular case, the model that was used was the Sacramento data. This is another famous model that was sort of used here. And this slide sort of shows you that if you just use the plain LSTM, which is it takes the weather inputs and spits out the soil, the stream flow, versus this architecture number 3 that I showed you, which sort of was handling multiple things here, you have much better performance. On the left curve here is showing the RMSE, lower the better. And this architecture number 3, STL architecture, has much lower RMSE for nearly every one of these 531 basin. And the right one is a different metric, which is called NSE, which is higher the better. And then you can sort of see that, for both cases, pretty significant improved performance. So with that, let me start with some concluding remarks that this is sort of showing this is physics-guided machine learning approach, or the scientific knowledge-guided machine learning approach offers a promising direction for addressing the limitation of pure ML or pure process-guided approaches. And again, these are all early works in this area. I mean, there's a lot of work in this area in multiple disciplines in the last few years, and most of it is in very early stages. And there's a tremendous opportunity to sort of work at this interface. And there are new ways people are trying to figure out how to incorporate complex physical knowledge into this architectures and the model learning framework. How do you deal with a model that has multiple components, interconnections, their interrelationships? You saw some of that in the slide. And one of the big things that sort of happens in many of these situations is that you have a lot of observations about this complex physical systems, not necessarily of the variable that you're trying to predict, but the other aspect of the system. And then how do you take them and assimilate them in your learning framework after the model has been built to improve the prediction. And this is sort of called the paradigm of data assimilation, and for bringing the traditional paradigm of data assimilation in the context of machine learning, or in this context of scientific guide, knowledge-guided machine learning is a big area of research. With that, let me just, here are some publications, work in progress. Mentioned to you this workshop. We held it in last August. We're going to hold another one of these in a virtual setting in August this year. And again, with that, let me just stop here and take any questions. Okay.
Thank you, Vipin, for this very interesting talk. And I'm inviting the audience to ask questions. Please use, if possible, the Q&A field, which should appear at the very bottom of your screen. Let me start with a question before we see the audience here. I was wondering, and I had asked you this before, how do you get an intuition for the complexity that's adequate or perfect for the physical problem? For example, even the depth of the neural networks, how many levels, how many neurons? And I know this is problem dependent, but maybe what's your, with the examples you presented, what's your thinking process?
Actually, a lot of that right now is done via hyperparameter optimization. So in the sense that there is so for example, I'll just give you many things. So even having the physics-based loss versus the training loss, the observation loss, how do you balance between them? That's a hyperparameter. Okay, you have so there are people are slowly trying to learn some of the methodologies behind them, but for the most part, many of these things are sort of handled by hyperparameter optimization, and which means you do need to make sure you have some setting in which you can test these different parameters and figure out what works. So I showed you a result for the Lake Mendota, for example. So we basically did a lot of we had to do a lot of hyperparameter optimizations to get sort of results that I showed some of the results that I showed you for that lake. And at some point, you sort of wonder whether these hyperparameters have been overly optimized for this particular system. So it's a very unsatisfactory situation. So basically, we resolved that in two different ways. So we froze the hyperparameters by the experimentation in some setting. And then we use the same hyperparameters then for almost 8,000 lakes that USGS have access to data, and to show whether this paradigm really works very well there. So when it was sort of working well in such a large scenario, then we had a lot more confidence that we haven't overtuned our setting just for one or two lakes for which we have a lot of observations. But that's sort of a limitation of these machine learning models. But except that, in the later part of the talk, I sort of showed you that there are some hardcore physical principles that you can bring in, right? This notion of state versus physics. It turns out that the variables like soil water versus precipitation to a machine learning algorithm that look like exactly the same thing, the number that you're feeding into a deep learning framework, but treating them differently, building the architecture differently, even though at a high level, you're still feeding only the weather drivers and some of these variables and then getting the output out, but incorporating them in the architecture and handling these different states and fluxes differently. It's something that's your scientific knowledge that's coming in to improve it.
Mm-hmm. So we have some audience questions.
Okay.
You might see them, Vipin, on your screen.
I can see.
You can also read it.
Yeah, I can see one of them.
This is from Everardo Olit. It's not exactly clear to me how we would input the physics loss into the loss function. Say for understanding the dynamics for a simple oscillator, would we somehow try to encode energy? How exactly would we do this for a dynamic system or materials discovery where physics-based approach isn't straightforward?
Good question. So exactly, okay, so I'll give you some sort of examples. So there are certain kind of loss functions that are extremely easy to incorporate. And those are the ones that depend purely on the output that you're predicting. Okay? So for example, in the lake temperature, if you're predicting the temperature of the lake at different depths, and you know the temperature translates to density, and density has to be consistent with the gravity, then it's very easy even for a computer scientist to take that information and create a loss function based upon that. Okay? So that's the simplest case. That is, there's a class of problems in which you just look at the output and you have a way of figuring out whether it's consistent or not. Second thing is that you have to compute some physical quantities to be able to be certain whether you're producing physical consistent results or not. And that was the situation that I showed you in the context of energy conservations. So for that one, this neural network, which was of course predicting the temperature, it also had to keep track of the energy fluxes coming in and out and the energy of the bowl at each time step. So it was a physics that was coded in that was sitting right next to the neural network, in the sense, but not part of the neural network code, but was sort of added on to the traditional LSTM code. Now you have to figure out exactly in your case, what would be the physics that you want to incorporate. Maybe your physics happens to be just some constraints among different variables that you're computing, which is what happens in the hydrology. You know, and I showed you some equations that in hydrology, the amount of water, the amount of precipitation, and amount of evapotranspiration, the water going into the soil versus the flow, all of them have to add up. Mass has to balance. So in some cases, if you look in the mass balance equations, in the case of simple oscillator, you may have a sense of exactly what is it, what would it mean for the output to be consistent. So what I'm saying that this is dependent on each application, but it's oftentimes it's not as hard. And if you read, as I said, we reviewed about 300 papers. There is a wide range of ways people are sort of trying to incorporate this physics into loss function. You have, if you're starting on this direction right now, you'll have at least 100 papers to look at in which people have incorporated physics into the loss function. So you at least, you will know what other people have done in perhaps not directly in your area, but in many related areas. Okay, hopefully that answers the question.
So another question by Zhangli Huang. Thanks for the excellent talk. When you add the physical loss as an additional constraint, have you tried to weigh the physical loss differently from the traditional loss function? If so, what were the outcomes?
Fantastic. You have to treat them differently. You cannot weigh them same. If you do, you will often do much worse for the target of interest, because these are two different quantities that are of very different nature. So there are two different approaches that you can use. One of them is hyperparameter optimization that I talked to you about, but a more recent and more powerful approach that sort of seems to work very well is look at the variance of all of these errors. You have two different kinds of terms. Each of them are varying at different times, and if you sort of modulate if you sort of balance the variance of these terms, you basically divide by standard deviation, it does actually a much better job. So there is a component of hyperparameterization there, but it's being sort of quote unquote eliminated or reduced in its sort of bad effect by some of this additional methodology that people have developed. And again, if you send me an email, I'll sort of direct you to some of the ways in which you can sort of try to do the balancing between these two losses.
See another question, but I would actually just a quick follow on. Can you recommend, we talked about hyperparameter optimization, can you recommend automated tools that you have experience with and you found useful in your own work? I recall a few in the community, they're bubbling up at universities, SharePoint and others. I was wondering what your take is on these automated
actually,
tools.
I don't have anything more fancy than what's available out there. The physical science community actually has very good tools for searching the hyperparameter. They don't call them hyperparameter. Basically, for parameterization of the model, they sort of have fancy tools. But the typical hyperparameterization tool that I have seen in the machine learning community are not necessarily any smarter than simple grid search. So it's pretty rudimentary, except that it's hard work, right? In the sense that I don't have a whole lot of information to give, except that there are, as I said, when you go to things like multitask optimization, then you have 6 different terms that you're trying to optimize simultaneously, and each one of them has a parameter in front of it. It's hopeless to learn all of those parameterizations simultaneously, which is where these techniques of making sure that the variance of all of these errors sort of remain within certain bounds does amazingly well. And again, people are still trying to understand the theory behind it, but at least that lets you get off, that lets you not worry about hyperparameter optimization, at least in some cases. But this is an important issue, and it has to be sort of resolved properly.
I'm not seeing any other questions, so last call for questions.
All right, I guess then it's the right timing.
Okay, then I think not seeing anything new. Yeah, many thanks, Vipin. It's very excellent talk, very informative, very inspiring.
Thank you.
Thank you for joining us here at the MIDAS seminar.